Hey everybody! Today we're going to work on learning the definition of continuity as it pertains to calculus. So at towards the beginning of the school year, we talked about continuous functions, but the way that we described them was they're graphs that you can draw without lifting your pencil from the paper, which is a pretty simple concept. But for calculus, we want like a more formal definition to describe when a function is continuous or when it is not. So that's what we're going to work on today. And this lesson ties limits into it as well. So the first thing I'm going to ask you to do is when you look at this graph, tell me, is it continuous or not? Well, this graph is not continuous because it has a hole in the graph. So if we were explaining this the pre-calculus way, we would say that this is discontinuous because there's a hole in the graph. Or you could say there's a hole at 2, 4. Okay? Now, the more formal definition for why it's discontinuous is because the function is not defined at this point. So we would say that the function is not defined at, and instead of saying at 2, 4, we're going to say this a more like calculus-y way, and that is to say that f of 2 equals 4. That's like another way of saying an ordered pair. So we're going to say the function is not defined at f of 2 is equal to 4, or maybe not even equal to 4 because it doesn't really equal 4 there. It's just not defined at f of 2 when x is 2. Okay, so the blue is like the pre-calculus way, and then the red is what we're kind of working toward today. Let's try another one. Why is this function not continuous? So we would say it is discontinuous because there's a jump in the graph. We actually call that a jump discontinuity. Okay, so that's how we would have explained it in the pre-calculus course, but tying into this intro to calculus unit that we're doing right now, let's see how we would do that. So if this is the calculus way of defining it, we could say it two ways. We could say that the function's not defined here because there's not like a solid point that exists when x is 3. So you could say that f of 3 is not defined. But we could look at it another way too. Do you see, like, obviously there's a jump in the graph because it's going steady until here and then it jumps up to this next section. Well, we could tie it into calculus by saying that the limit as we approach 3 from the left side is not the same as the limit as we approach 3 from the right. And if our limits are not equal, that means your graph is not meeting up at the same location. So we're going to say that the limit as x approaches 3 from the left of, oh, it's not f of x, it's g of x, of g of x is not equal to the right-hand limit. Okay, so this is just another way of you being more formal, but another way of you saying, like, these two lines don't meet up in the same place, okay? So the blue is what we would have done in pre-calc, and then the red is more of like that formal calculus definition. One more. So is this graph continuous? No, it's not continuous. This one is also a jump discontinuity. And this one actually has a more specific name. It is a graph that jumps, but it has a more specific name called an infinite discontinuity. And that's because the graph goes to infinity on both ends of this asymptote. So we would call it an infinite discontinuity to be more specific. All right, so let's think about how we could define this one. So why isn't it continuous? The calculus way, we could say option 1, it's not continuous because there's no point at this split in the graph, like f of 3 doesn't exist. So I'm going to throw out some different notations that we did like last section. So f of 3 does not exist, D and E. Or we could do that same explanation as before, and we could say that the left-hand limit and the right-hand limit are not equal to each other. So I'm going to say the limit as we're approaching 3 from the left of h of x is not equal to the limit as we approach 3 from the right. Okay, so let's tie it all together. Here's the formal definition for how to prove that a function is continuous. Now, when I say prove, I don't mean like you're going to look at a graph and say, oh, that's a smooth curve, or that's a line I could draw without picking up my pencil. That's not proving, that's just a visual aid. Proving is going to be where I give you a function in equation format only, with no graph, and you're going to have to be able to tell me if that function is a continuous function solely by looking at the equation. Okay, so it's a 3-step process. The first thing you're going to do is you're going to see if the function is defined at C, and C is going to vary. This will be like the point of continuity that you're focusing on. Okay, in the last 2 examples, that C value happened to be 3 because that's where the asymptote was or the hole was. So the point of continuity or discontinuity, is just like the point where it looks like something weird might be going on, and you'll see here in a second what that means. So first you're going to prove that f is defined, meaning there is an actual point on the graph there. Then you're going to say that prove that f has a limit. Okay, so now there's a second part, or like a sub part to this. If f has a limit, that means that the limit from the left and the limit from the right are equal. So that's what we would be proving here. We would be proving that the left-hand limit and the right-hand limit are the same, which means that there is a hole limit at that point. So that's step 2. And then step 3, you're going to prove that the limit is equal to where the actual point is on the graph. So you're going to say that the limit as I'm approaching C is the same as f of C. So this would be like the ordered pair at that point. And then the limit is like what you're approaching. All of this is going to make a lot more sense when I show you a visual, hopefully. Okay. Oh Lord, come on, strobe. Okay. All right, so here's what it might look like. So notice there's no graph given. I just am asking you to prove that the function is discontinuous at 3. So that would be your point of continuity or discontinuity maybe. This would be called your C value. Okay, so step 1, and you're going to go back to that definition on the last slide, is prove that f of C is defined. Okay, so what I'm going to do is I'm going to take C is 3, so I'm going to find f of 3. And f of 3 is going to be determined by finding which of these functions in the piecewise function contains 3, which would be this one because this has the equal to line, and then plug that number in and just make sure that you get an answer. So it's like you just don't want to get something that's not computable. Well, if I plug 3 into this function, I would get 9. That is an answer. So f of C is defined, meaning part 1 of the continuity proof is good to go. So then step 2 is we're going to prove that the limit exists, which means does the limit as we approach from the left equal the limit as we approach from the right? okay? Now, this is not as easy as reading a graph because we don't have a graph. So we're going to have to think about the different skills that we obtained when we were learning about limits for what you can do when you don't have a picture in front of you. And one of those skills was plug and chug. So if I'm asking you to find the limit as x approaches, c is 3 from the left, you're going to go up here and say which one would be approaching 3 from the left. Would be the bottom one because this is number smaller than 3. So you would be saying, what is the limit as I approach 3 from the left for x squared? And you're going to just do a plug and chug. So if I plug in 3 into x squared, I get 9. And then I'm going to say, okay, I also need to do my right-hand limit. So which function would I use if I'm approaching from the right? The top one, because that's for values that are greater than 3. And if I plug in chug here, I get 3 minus 3, which is 0. Okay, so step 2 in the continuity proof is incorrect or null and void, basically because the left-hand limit, so the limit, I guess we could just say that the limit as we approach 3 does not exist, because the left-hand limit and the right-hand limit were not the same, meaning your points of your graph at that location are not meeting up. I have a visual aid for you right here. Here's what the actual graph looks like, and you can tell that if I have a limit as I'm approaching 3, which is here, from the right I'm getting 0, and from the left I'm reaching 9, and those obviously don't match up, and that means that the graph can't be continuous if you have two different limit values at the same point. So you would say this function is discontinuous. You've proven that because the second part of the requirement did not work. Okay, 2 more examples, and these are going to be like what you're going to see on the Delta Math assignment. So it says use the definition of continuity to determine whether the function graphed below is continuous at -5. So like this first example I think is kind of easy because it gives you a picture and you're kind of just following the picture. So it says since the limit as x approaches -5 from the left, so that equals, they're saying what does it equal? It equals 1. And the limit as we approach -5 from the right also equals 1. It can be determined that the limit, the whole limit does exist, so you would want to say exists, and is equal to 1. So I'm saying that since these two limit values are the same, then the whole limit is also equal to 1. Furthermore, it can be seen that f of -5 equals, and that would just be like what's the ordered pair at -5, which is also 1. Therefore, it can be stated that the function is continuous. That would be the option you would choose at -5, and then there would be a reason here that you would state. Okay, here's the other type of question you're going to see on your Delta Math. This is the same thing, but you're doing a lot of work behind the scenes to figure out this answer. And I will warn you, you only get one try on these, obviously, because there's only 2 options. So take your time, and this is being graded for accuracy. So this is where you're going to go through and you're going to prove the 3 different conditions of the continuity proof. So you're going to say, is f of c defined? Meaning, can I plug 3 in and get an actual answer? Yes, I can. I would get, what, 9? Is the limit equal on both sides? So is the limit as I approach 3 from the left, does it equal the limit as I approach 3 from the right? Which you're just going to do a plug and chug deal to see if that works. So if I approach 3 from the left, that'd be the bottom row. Plug in 3, 15 minus 3, that would be 9. And the right side, the top would also be 9, so that works. And then the third step, which we haven't seen, is does f of c equal the limit? Well, f of c was 9, and the limit was 9, and yes, they are equal, so that's also proven. So this would be that the function is continuous.